group. Uh, I've been told I am actually in the West Coast right now. I'm in Victoria, and I've been told we are having unseasonably warm weather here. But every time I come, it's super nice. So I am shocked that is a thing. Hi, David. David and I were out last night observing at the Victoria Center's telescope. It was so fun.
And did you see Jupiter?
I saw Jupiter and I saw the bands on Jupiter. It was so cool. And all the Galilean moons. Didn't see the Great Red Spot, but you can figure out why I didn't see that. Yeah, we saw Jupiter and we saw Andromeda, and we saw the Ring Nebula. That was really cool. They have a nice 12-inch out here, but we weren't looking through the 12-inch. We were looking through the refractor. David can tell you in the chat. The Ring Nebula, yeah. And I was out to the Sunshine Coast and I saw their setup as well too. Makes me want to move out here. Okay. I think we have, I don't want to go home to Kitchener-Waterloo now. It's cloudy and rainy. It's beautiful skies out here.
Yeah, it was cloudy last night in the GTA.
It's so funny. People out here are complaining about the light pollution. I'm like, you haven't hung out in the GTA for long enough. Okay, let's get started. So welcome everyone to Insider's Guide. We're back to bi-weekly sessions, and today we are going to be doing Variable Stars Part 2. So everything we didn't cover in last week's episode, speaking of which, you haven't seen last week's, go back 2 weeks ago. Go back on YouTube and watch it, and then come back to this one, or sit and watch this one, and then go back after. And without further ado, I'll let Chris take it away.
Yes, thank you. Yeah, so when I put my notes together for Variable Stars, I took a look at the document. I said, oh my, we need 2 sessions for all this material. So we split it into 2 halves and we'll finish it up today. So what we did last time is I talked about the general idea around variable stars, a bit of the history of how they came to be recognized. We talked about the 2 main types. There are intrinsic variable stars and extrinsic variable stars. So extrinsic stars are ones where the star itself isn't changing its brightness, but something is causing its light to vary from our perspective. So the variable star Algol and Perseus was the prime example of that. We went over that. And then this time around, we're going to talk about the intrinsic variable stars, where the star itself is doing something that makes it appear to change its brightness from our perspective. So we'll go through that. I also talked about the system for naming variable stars last time around. So I'll try to operate as if, not assume everybody saw last one, but hopefully everyone has. Then after I finish talking about intrinsically variable stars, then we'll spend some time looking at the various tools you can use to get into it for yourself, looking at variable stars for yourself. There's lots of resources online for doing that. So it's a lot of fun. And then at the end, we'll wrap it up with 5 more Messier objects for the autumn sky, leaving only 4 left to finish the set on our next session. So here we go. So as I mentioned, I'll start sharing my screen here. And hopefully my internet is better this time than it was last time. Here we go. Okay. So what I'm going to show you is this chart. So this is a sketch of the Hertzsprung-Russell diagram that describes, basically just organizes stars into their various domains according to their evolution and their mass and so on. So across the bottom, we have the spectral class, which roughly corresponds to from high temperature to low temperature. And then we have their brightness, absolute magnitude here. So of course, the big stars would be the bright ones, and then the small stars like white dwarfs would be the faint ones. Now, most regular stars spend the bulk of their time on the main sequence. And when they get old and things start to age up, they've fused a lot of their hydrogen into helium, the internal composition of the star starts to evolve towards their ultimate end. And as they do that, they tend to migrate up off the main sequence, and they run through this sort of transition point here. This is called the instability strip here. And this is where you find lots of the different variable stars, the kind that are intrinsically variable because the star itself is rocking and rolling, doing various things as it ages up and evolves. So this is one simple sketch off Wikipedia for, you'll see some names that we're going to talk a bit more about here in a minute. And then there's a more complicated version of the same sort of diagram, which divides up some of these types. So all of these things, the RV Tauri, W Virginis, RR Lyra, Delta Scuti, these are all different different types of variable stars, not all of which we're going to cover because there are some of these where they do vary, yes, but not enough to really be noticeable to beginner astronomers. You know, if you're going to do photometry and measure their brightness or, you know, get into the details, then yes, you can detect the variability. But if you're a casual observer, you want to look at the stars that you can notice vary, then some of these will work for you and some won't. But we'll get into a little bit more about that here in a minute. So
we just had a quick question.
Yep.
Where would we place the sun on this chart?
Yeah, the sun is a G-class star, so it falls under the column G here, and it's on the main sequence still. So it's a middle-aged star, hasn't started to evolve off of that yet. So it'll stay here for another several billion years, 4 billion years or so, and then it'll start to meander its way off the main sequence. So good question. All right, so as I said, you know, a lot of these intrinsically variable stars are doing this because they have evolved to the point where they're no longer at a stable state fusing hydrogen in their cores. In some cases, their hydrogen has been depleted, or in other cases, the helium has risen to a high enough concentration to start affecting things. And basically what's happening in general terms, and again, we're going to be speaking kind of rules of thumb today. We're not going to get into the equations and the details, but generally what's happening is that something inside the star is causing it to heat up. Generally, that will make the star expand or swell in size. When the star, you know, volume increases, its surface area increases, and so more light is shining from every square meter of that star, so it looks brighter when it's larger, generally speaking, in visible light. And then whatever caused that pressure and that swelling to start generally has a release mechanism that lets the star revert back to the smaller form and dim again. So you get this almost like a steam engine or even a internal combustion engine where you've got pressure building, does some work, gets released, and the cycle begins over and over again. So these stars cycle on a periodic basis. And generally speaking, this pulsation effect is happening in the, at some point in the interior of the star where it's still squishy. So if you think of the center of the star, the core of a star, as being almost so dense and so hot that it's almost degenerate, where the atoms are so crushed together that it can't really move or do anything. And then you've got your outer skin of the shell of the star, the photosphere sort of region, where it's much more tenuous. And in between those two regimes, you've got what I would think of as kind of the squishy part of the star, where material can actually convect and move around and cycle through those intermediate layers of the star. And that's generally where a lot of this action is happening. So the first one I want to talk about is Mira. So if you watched our last session, I mentioned that Mira was one of the first stars to be discovered to be variable or noticed to be variable. And again, for all we know, the ancients noticed stars were varying in brightness long before modern science noticed them. So here's Mira. And Mira is visible in the evening sky. So it's just rising kind of in the southeastern sky. I'm just going to put my clock on here so everybody can see my time. Oops, wrong one. Let's go up to my clock. Here we go. So this is the sky around 11 p.m. to midnight tonight's sky. You'll see the moon is hanging up there near the constellation of Cetus. So Mira is the star that's in the kind of the center of the neck of the sea monster. So it's otherwise known as Omicron Ceti. And Mira is a pulsating star. Mira is actually a reddish looking star, and it's very late evolved. So it's a star similar to our sun, not too massive, that is very, very far along in its evolutionary process, to the point where it's gone, well up that bridge, that instability zone, and heading into the red giant part of the HR diagram. And what you have then is that the star itself swells to much bigger size than it originally was as it's evolving into the red giant phase. And so and ultimately that kind of a star will eventually turn into a planetary nebula, with a white dwarf center, that kind of thing. So we're still understanding a little bit more about why this is happening, but essentially we think is that because there's a mixture of the hydrogen fusing in the core inside the star, as well as helium, which is able to fuse once it gets to a sufficient concentration, that there's an alternating process where sometimes the hydrogen is fusing in a shell, and then sometimes the helium takes over and it's fusing in its shell. And that alternating process causes the star to swell and contract, swell and contract. So a variable like Mira, we call these Mira type variables. They oscillate over periods with 100 or several hundred days. So it takes a while for that to happen. That alternating fusion process in the star actually produces a lot of convection and mixing. And there's actually a term called dredge up, where material is being actually stirred up. The interior of the star is being stirred up, and that keeps the process going. So basically the entire star expands and contracts. As the star cools, it contracts, and the energy output that we detect from the star actually swings from infrared to visible. So the star is changing in brightness. The star's luminosity is changing, but the star's visible in brightness is varying because we're seeing more visible light at times and then less visible light because it's becoming more infrared light. And so it's alternating back and forth, and that produces the change. You get about 2.5 magnitudes worth of brightness change in this type of star. And so a couple more notes. It's most luminous when the star is its smallest radius and hottest, and it brightens while it's cooling. So I've got a light curve for Mira here I can share. Just open that one up. So here's the effect happening. So you see the star is dimming, and then it brightens up, and then it dims and brightens up. And it's more of a sawtooth than a nice sinusoidal effect. Remember that the Algol type stars with the little orbiting companion, they tend to do a notch in a steady state. And these pulsating stars tend to be more sinusoidal or sawtooth in effect. So you can head out and you can check out Mira. It varies. I'm not sure where in the cycle it is right now, but we can look that up a little bit later when we get to our AAVSO section. Other stars that do this, Mira type variable, include Chi Cygni. I think I got Chi Cygni. Here's Chi Cygni. So Chi Cygni is in the neck of the swan. It's not a very bright star though. So whereas Mira's basically naked eye star when it's near its peak, and then fades to invisibility when it's faint. Chi is a less prominent star, so you'll need your binocular or telescope to pick this one up. And there's another star that does the same effect. That's R Cassiopeia, which you can look up on your own, or we can check it out later if we have time. All right, so that's the Mira type variable. The next one, the next famous one everybody's heard of, are the Cepheid variable stars. So let me just bring this guy up. And now we're facing north. And let's go back to tonight, actually. I've got my date changed here. Go back to tonight. So Cepheus is kind of climbing the eastern half of the sky when you're facing north in late September. It's got this box shape and then what I think of as kind of a pointy roof aiming down roughly towards Polaris. And in the upper right corner of the box, there's a little group of stars. Just zoom in on here. So this little triangle of stars. You can see this with your naked eyes. And there's a star Zeta. There's a star Epsilon. And then at the bottom of the triangle here, Delta. Now, because Cepheus is a circumpolar constellation, you know, its orientation will vary throughout the night, throughout the year. So essentially, you're looking for the opposite end to the pointy hat or point or roof peak down to the bottom corner. The corner that's sort of nearest to Cassiopeia. So there's W-shaped Cassiopeia. So if you kind of orient these two, by the way, these are husband and wife in mythology. So we get these three stars, Zeta, Epsilon, and Delta. And Delta is a Cepheid variable star. So it's the one that gave us that term, Cepheid variable. It was discovered, I mentioned when it was discovered in our last session way back when. So what's happening here, this is a type, Cepheid variable stars come in two different types. Type 1, which is the classical original type, and then type 2. So Delta Cephei is the type 1 star, and it's a metal-rich younger star, population 1. They're called the stars that arose later in the evolution of the universe. It's got these stars typically have between 4 and 20 times the mass of the sun. They're 1,000 to 50,000 times more luminous than our sun, and they're considered to be bright giants or low luminosity supergiants. The spectral classes tend to be in the range of F through K, sort of in the middle of the road color-wise. So as I said, they start pulsating after they evolve off the main sequence, after they've developed, accumulated helium in their core. And we think the process of making the star pulsate is not like the Mira red giant, where it's varying its radius by a lot. What's happening in the case of the Cepheid variable, the Delta Cepheid variable, is that there is energy being produced in the core of the star, and that energy is heating up the helium that's into the mixture in the center of the star, and that energy ionizes the helium, and it can singly or doubly ionize those helium atoms. And when the helium is doubly ionized, it becomes very opaque to the energy. And so as that energy builds up, you get more doubly ionized helium, that blocks the energy from escaping the interior of the star. And so then the star heats up and swells up somewhat. So that trapped heat, it builds up, the star swells up. Eventually, it swells up to the point where as it swells, it cools down. That allows the helium atoms to become stable again, to deionize, and then they become transparent to the energy and the light, and then the star can cool and shrink again. So that builds up and down. Now, what causes the star to collapse again is basically its gravity. So it's self-gravity just collapsing it down. There's a light curve here I can share for this type of process. You'll see it's similar. So here we go. So we have the energy building up, the star gets bright, and then it more gradually dissipates. Now, way back in, and I'll keep the stellarium on here so you can see what we're talking about. So way back in 1908 or so, between 1908 and 1912, Henrietta Swan Leavitt, who worked at the Harvard Observatory, she was analyzing the stars in the photographic plates that the observatory were collecting, and she eventually discovered a relationship between the period of variability of these type of stars and their luminosity. And so what she was able to do, and she was using mainly stars in the Magellanic Cloud, where there were lots of them, to photograph on a single plate. And this allowed her to develop this formula that told her that if she knew the period of variability, then she knew how bright the star should be, the absolute brightness of the star. And by knowing the absolute brightness and comparing that with the apparent brightness, she could estimate how far away the star was. And that then allowed her to start putting yardsticks on the night sky. And basically, she was developing what we call a standard candle. So there are different objects in the universe that we know how bright they are, we know how bright they look, and we can tell from that how far away they are, and they give us these measuring sticks in the universe. So that term standard candle came about. So a few years later, in around 1918, Harlow Shapley, who was also at the university, he started to use those Cepheid variable star relationships to find them in our Milky Way and plot where they were coming out, their distance and their directions, and kind of mapping out or piecing together the puzzle of what our Milky Way galaxy was shaped like. And so he's kind of credited with coming up with that sort of disk shape to our Milky Way galaxy. Then sometime later, Edwin Hubble, working in California, he was discovering Cepheid variable stars in the Andromeda galaxy, which was then thought to be a nebula. We didn't know it was a galaxy at that point. And he actually estimated that nebula was about 929,000 light years away, which was way off. It's about 2.5 million light years away. So he was able to start figuring out that it was a separate galaxy altogether, and he was doing this with other galaxies as well. And then in the 1930s, at Canada's David Dunlap Observatory, Helen Sawyer-Hogg was working there and taking images of globular clusters and determining their distances by finding the Cepheid variable stars in them. So back to delta, if you want to look at it for yourself. So delta varies from magnitude 3.48 to 4.37, which is more than a factor of 2, exactly every 5 days and 9 hours. And what that means is that when it's at its brightest, it's the same brightness as zeta. And when it's at its dimmest, it's the same brightness as epsilon. So it's a super easy one to check. Any night you're out, look for Cepheus, find that trio of stars, and then see whether delta resembles more the brightness of zeta or the brightness of epsilon. And you can then immediately judge where in the cycle it is. So that's a cool one. Another good one that you can do the same sort of trick is over here in Aquila. So here we have Aquila. We've got the bright star Altair, which is part of the summer triangle. And then you've got your more easterly wing and westerly wing and the tail of the eagle. And the star that's halfway, kind of at the elbow of the easterly wing of Aquila is Eta Aquilae. It varies from 3.48 to 4.33 over 7.18 days. So it's about a week. When it's bright, it's the same as the tail. And when it's faint, it's the same as this little Iota star that's tucked kind of halfway between them. So that's another very easy one for you to look at for yourself. All right, I'll stop talking for a second, see if anybody had any questions.
Perfect. I was actually going to interrupt you right now for questions. So I was going to make a comment, which I was talking to someone last night, and I mentioned that Polaris is actually a variable star, and it's a Delphic, it's a classical Cepheid variable. It's actually the closest one to Earth. So that is a cool fact you can throw out to people. It's not only our North Star, but it is a classical or type 1 Cepheid variable.
Yeah.
The two questions we have are kind of related to what we've been talking about. One, just going back to the stars, how do we determine whether a star will become a black hole, a nebula with a white dwarf, or will form a supernova? What's the characteristic of the star?
So the general rule of thumb is how massive the star is when it was born. So if a star is formed roughly the size of our sun, or within, I think it's about up to 7 times the mass of our sun, it won't be big enough to have a runaway collapse at the end of its life and either make a neutron star, supernova, or black hole. So the stars that are within, say, this a little bit between the smaller than the sun up to 7-8 times the sun, maybe 10, I forget. They'll turn into planetary nebulae, and the planetary nebulae is formed when eventually the envelope of the star blows off, leaving the exposed hot core, and that's the star we see as the white dwarf in the center of the planetary nebula. Mm-hmm. So if the star is much more massive when it's formed, tend to be the bright hot stars that we see dominating the winter sky, the Rigel and Procyon, Sirius, these hot big stars. They're more massive, and then when they get to the end of their life cycles, they collapse under their own gravity catastrophically, and they blow up and form neutron stars, black holes, supernova. I think that's
So, yeah, perfect. The other question we have is kind of comparing our sun to what we've been talking about so far. We did discuss, they were asking where in the stage as our sun compared to the stars being discussed. And I would like to point back to I've shared in the chat, the first link I shared was how the variable stars plotted on the HR diagram. And our sun's on the lower part of the main sequence. So if you really want to compare kind of the ones we've been talking about, that's probably the easiest way to do it. But our sun, I'm assuming, does not vary in brightness, does it, Chris?
So I think every star fluctuates in brightness to some degree, and there's an entire field of science around the various mechanisms that produce that. And there could be a whole variety of reasons that are to do with their shape or their chemistry or their, physical structure, or their degree of evolution. And so, if you want to pursue astronomy as a career and you're ready to pick your PhD thesis, it can be the most fascinating little niche about, why a star varies by a tiny amount that you can't see with your eye, but you can measure with an instrument. There's all kinds of great details in science like that.
Mm-hmm.
Yeah.
And the last is, what's the difference between stars varying in brightness and sunspots? Because I don't think sunspots actually affect the brightness of the star, do they?
They can, yeah. In fact, I think I'm going to mention that towards the end of the first section of the topic here. Yeah.
Sorry,
so
I skipped ahead.
And no, that's okay. So any part of the star itself that can actually dim its light output can affect cause it to vary. So yeah, that's one example. Just by the way, if you're using Stellarium and you do select a star and you do have the fair bit of information, you can vary the amount of information that gets shown when you show a star. But one of the parameters it's got here is magnitude range, 1.86. It's got a dividing sign, I don't know why, to 2.13. So that's the variability of Polaris. And that would be, it's less than an integer amount, much less than an integer amount. So it's, maybe 50% more bright, or, I'd have to look it up. But yeah, it doesn't vary by a tremendous amount the way those other two examples I gave you are, but it does vary. Okay. So let's press
Move on to type 2.
Yeah. So type 2 Cepheid variables they tend to be lower mass, metal poor, which means they were formed early in the universe's evolution when there was less enrichment of the heavier elements. So they're called population 2 stars. It's kind of strange that the population 1 stars are the young stars and population 2 stars are the old stars, but that's the way it worked out. They pulsate, so these type 2 Cepheid variables, they pulsate between 1 and 50-day periods. They're broken up into 3 subclasses. So you've got short period ones that vary over 1 to 4 days. Those would be examples like the star BL Hercules. Then you've got a medium period that varies between 10 and 20 days. And one example of that is W Virginis. And again, you can make a note and look at these in the springtime when they come back. And then the longer period variable would be more than 20 days to cycle. And that would be RV Tauri, would be one of those. It'll be coming up in the winter sky in the next weeks and months. The star R Scuti in the constellation of Scutum, it's one of those long variable stars. I think I've got it. Here we go, R Scuti. So this is the tonight sky around 10 p.m. looking southwest. So there's our Eta. So that's our Eta Aquila, the Cepheid type 1. And then we have R Scuti, which is the Cepheid type 2. And it's down here near the wild duck cluster. So there's the wild duck cluster right there, which you can find in binoculars. And then just look probably a finger's width or so, maybe a thumb's width. Yeah, just a finger's width to the right, and you can find R Scuti. So there's the brighter star beta just above, and then less than a finger's width below is R Scuti. So R Scuti varies from magnitude 4.2 to 8.6, as you can see here in the stellarium. So that ranges between naked eye to needing binoculars. So if you don't see it with your unaided eyes, then it must be towards the minimum at cycle. It takes 145 days though. So it's one of those long variables. And generally speaking, these type 2 Cepheid variables have less regular light curves to them. Okay, another type of variable star, intrinsically variable star, RR Lyrae. So here's the constellation, here's the summer triangle. Most of it anyway. There we go. So Deneb, Vega, Altair, tonight sky around 9 p.m. So if you go up to the upper wing of Cygnus the Swan and kind of look for the elbow in the wing on the side towards Vega, towards Lyra, then this star is RR Lyrae. It's similar to a Cepheid variable star, but it's a bit different. It tends to be older than type 1, but younger than type 2. So it's kind of intermediate. These ones were discovered by Wilhelmina Fleming at the Harvard Observatory, another of the famous female astronomers that we all need more credit. They also have period luminosity relationships, RR Lyrae stars, but that occurs more reliably in the infrared than in the visible. So if you monitor them in infrared, you'll see that more variability. Here's a variable, here's a curve. I'll just open one up.
Just
so you can see,
quick, oh, sorry.
Go ahead.
Somebody noted that your stellarium is on the 13th, not the 27th, but this would just affect exactly when things would be up in the sky at a certain point. So you'll still be, if you see these, Vega and the Cygnus, you'll be able to see it still relatively the same spot.
Yeah,
as
the
Chris was pointing out.
2 week difference won't make any difference to your your observing. Thanks. Yeah,
So
I created the bookmarks back when we were doing last week's session.
Yes, and I figured I just wanted to tell everybody it's okay.
Yeah, no panic. Let's see. This one varies over, as I said, 7.06 to 8.12. So it's about doubling and halving its brightness. And its cycle is only 13 hours and 36 minutes. And what's neat about this type of star is that each pulsation causes the star to vary between about 5.1 to 5.6 times the sun's radius. So it's about 10%. So we did our Mira stars. Let's get into eruptive type stars. So stars can get bright because they suddenly erupt in brightness. Examples of that would be the star RS Ophiuchi. So if you look up lists of recurrent novae, a star like RS Ophiuchi would be an example of that. It did an outburst in 2021. It does a fast brightening and then a long, long decay. And I'll show you how a light curve of that one. There we go. So unlike, many certain types of novae will flare up and then take a long time to fade in brightness again. So most of the time it was sitting here at magnitude 11, which you'd need a telescope to see. And then suddenly it flared up to magnitude almost 2, which is easy naked eye brightness. And then that took, I think it was over a few weeks, faded down, and then over several months, eventually it reverts back to its original faint brightness. So that just happens from time to time, unpredictable exactly to when. So there's actually a list of the eruptive variables here. Let me see if I can find this one. Hibernate. So if you hear in the news or on a RASC forum that a certain star is in outburst, then it's worth an effort to take a look. Check it out. I went out and saw the RS Ophiuchi with my scope, and it was really fun. So here are all the different historical years where it outburst. So you can take a look at that. That's another type. How's our time? Good. Next up, we have R. Coronae borealis, or Variabilis coronae is its other nickname. So this is a eruptive type star, but instead of flaring in brightness, it drops in brightness. So it's kind of a reverse nova, if you want to think of it that way. So normally it shines about magnitude 5.7, and then now and again it'll fade down to obscurity, to magnitude 14. And that is because opaque carbon soot is developing in the star's atmosphere, and that soot is just blocking the visible light from getting to us. So the star tends to drop in brightness rapidly and then slowly recover over time. So that's a neat one. That's in, as I said, if I go to the 26th, 27th here, here's tonight's sky, and you'll see it's sitting above the western horizon around 9 o'clock below Hercules, and this star is inside the crown shape of Corona Borealis. So odds are when you look at it, it'll just look like it always looks, but every now and again it'll disappear on you. So you, again, it's one of these where you need to kind of listen to the rascals and see who's reporting that it's collapsed. All right, last up, and I'm not going to get into a lot more details about the novae and supernovae, but basically we talked about the planetary nebula forming and the white dwarf remaining in the center of the star. So if you do get a situation where a sun-sized star is in a binary system with a more massive star, then it's possible for that white dwarf to sip matter off the companion. And if enough matter gets transferred from the companion to the white dwarf star, it can experience a catastrophic flare of fusion in a runaway effect that causes it to flare in brightness until that material is consumed, and then it'll go quiet again. So that's called a type 1A supernova. And we know the exact mass threshold that they have to reach for them to flare. So they're another example of a standard candle that we can use, because when they flare up, we know how bright they should be. All right, and they're about, so as far as standard candles go, we can see type 1 supernovae out to about 500 times farther than we can Cepheid variable stars. So Samantha, if you want to share that link on the article on rasc.ca, I found that one late in the process, but it's a
I was
nice
literally
overview.
just copying and paste it, so it's all there. Just a reminder, our YouTube friends can see everything in the description box, and if you miss any of the links I share in the chat during the Zoom, then it's always going to be in our YouTube description box as well, if you go back to that week's video.
Perfect. Okay. Any questions?
Got one just popping up. Assuming that debris is everywhere along with larger objects such as asteroids and meteorites, do they crash into and absorb in our sun and other suns? What happens to the star when this happens?
Sorry, I think I missed the beginning of that. So that we're talking about
what happens when space debris hits the sun or a star.
Yeah. Well, things fall into the sun all the time. It's just that they're so tiny compared to the mass of the sun that they have negligible effect, basically. There are some really nice animations that you can find from NASA and European Space Agency of comets falling into the inner solar system and just constantly raining down into the sun all the time. And it happens every day that a comet or something hits the sun. The sun doesn't affect the sun at all, shrugs it off.
So that couldn't be a reason for variability then?
No, it shouldn't have any effect. Cool.
Okay. Any other questions before we move on to actually tracking these light curves? Okay, I think we're ready for you to move on.
All right, so what I'm going to show you is I'm going to walk you through kind of a tour of the website of the American Association of Variable Star Observers, AAVSO. And this is a fantastic organization. Their specialty are variable stars. You can join the organization. You can create an account on their website. I'll show you why you might want to do that here in a bit. And what they do is they promote the concept of observing variable stars. They gather the data from people that are interested in contributing to science by observing variable stars. And it's a great place to go to get started on. Before I get too more deeply into that, I just wanted to mention that we do talk about variable stars in every year's Observer's Handbook. So there is a table of long period variable stars observable in Canada in the handbook, on the brighter end of things. And every year a variable star is highlighted. This year, the variable star that's being highlighted is the Corona Borealis. So this is a pulsating variable star, varies from magnitude 6.9 to 12.6. So if you have your Observer's Handbook for 2022 handy, you can turn to that page. It's around 298 or so in the handbook, and read about that star and how to go about looking at it. All right, so back to AAVSO. So first up, you want to go to the education page. So you can see here we've got a number of quick links to different parts of the website. So there's a section called Education. You go on in here, you'll find that there are online courses, observing manuals, lists of variable stars, and videos. And if you go down in here a little bit, you've got a section for observing for beginners and then more experienced observers. And there's a 10-star tutorial to get you started. There's a list of easy to observe variable stars. So this has got the name of the star, its type. If you scroll down here, you can see the different types. So Mira, RV Tauri, semi-regular, and so on. You've got the magnitude range. Of course, small number means brighter, big number means dimmer. And you can look for the easy ones to see are the ones with smaller numbers. So magnitude 2, that's our friend Mira, Omicron Ceti. Chi Cygni, that's the one in the neck of the swan that I showed you a little while ago. And there should be a few others in here that we've talked about already. Here's the period in days that it varies by. And then these suggested charts are the finder charts that you can make on this website, varying from A, which is a wide field, down to B and D and E, which are more telescope eyepiece fields of view. And then you can also look at the finder chart for each one. So if I were to say go down to the Cygnus chart here, it shows me the constellation, and then it's labeling which stars are variable with these little circles. So instead of black dots for the stars, you've got the little open circles. There's Chi, that's the one in the neck of the swan I talked about. And there are a few others around as well. So there's that. What else? Then you've got binoculars program that you can use, you can see with your binoculars. So down here is a list of stars that are easy to track by using binoculars. And we'll come back to using binocular and making charts for binoculars in a bit here. And let's see. Let's get into the more tools now. So we're going to go into the tools and observer resources. So we've got a page called For Observers, and here we've got big icons that are links to portals into different web pages. So the first one up here is the light curve generator. So let's go into the light curve generator. And here's where you're going to type in the name of your star and plot its curve over time. Now, there's a tricky thing about using the AAVSO, and that is that you can't type the regular star. You can't type Albireo. You can't type Polaris. Okay, you have to look up what its other designations are. So for example, they like to accept the Bayer designation. That's the Greek letter plus the constellation. So if we type in Alpha Umai, that should work. That's Polaris. Not much to see there. Let's go back and do another one. What are you going to say?
Oh, sorry. No, I was laughing at how small Polaris's variability is.
So let's see. How about, let's see, pick another one. Oh, and by the way, when you're typing in the Greek letters, they have to be 3 letters. So ALF, BET, GAM. When you get to the Greek letters that normally we have 2 letters the way we spell it, they add an extra letter. So for mu, instead of MU, it's MIU. And so for anyway, there's a list here of you can put the link in the chat with the Greek letters and it tells you the right way to spell the letters. You can also put in the Stellarium HIP number, so HIP 77501, or the HD number. So it'll accept most of these numbers. It's just if you're going to spell it out using the Greek letter, you've got to get that right. So let's see. What was that? That was HIP. Find that one again. HIP 77501. Let's try that one. HIP 77501. And there we go. So what you've got here is a plot versus days. So brightness versus days. And you've got different types of observations in here. So all of these little blue check marks are plotted with different symbols on the graph. Now the Julian days are just basically counting up the days of the year cumulatively over time. If you go into Stellarium and you go down to your date and time tool, the tab that nobody ever uses on the right here is called the Julian day tab, and that is giving you the Julian date. So it switches over at midnight Greenwich time when it's .0000 minute midnight Greenwich time. So you can convert whenever you want to convert local time to Julian date. You can go and use Stellarium for that, or you can go back to this chooser again, and you can actually ask it for calendar dates if you wanted calendar dates instead. Okay, you can ask it for all the bands, or you can select certain bands. In this case, I asked for all of them. And in terms of the range of time that you want to plot, it has a default amount, and you can also specify how many days you want it to plot. If you click all, then it plots all the observations in the database, and it could take you a few minutes for it to load up. So better just to set HIP, was it 77501? Is that the one? There we go. And once you're here, if you want to, you can actually switch on and off these observations just by clicking the check mark on and off. That's neat. When you're here as well, you can actually click this mean diagram. You can actually smooth the curve if you want to play with that as well. So eventually you'll get to a nice point where it's kind of fitting the curve smoothly. So that's kind of fun. So any of the variable stars that we've talked about last time or this time, you can put in here. So MIU SETI should work. Maybe I got it wrong. MIU SETI. Maybe there's nothing in here for it. Yeah, so that's plotting a light curve. Let's see, anything else to say? Okay. Any questions on any of that? Samantha, anybody else?
I don't see any questions. Oh, Omicron Theta, someone just mentioned in the chat. I think they want to see what that looks like.
Oh, Omicron SETI, okay. OmiSet, that should work. There you go.
That's interesting looking.
Yeah. So that's that sawtooth effect that I talked about, showed you from Wikipedia. So a lot of those Wikipedia light curves that I shared on the screen were taking these data sets and collecting just, say, the visual wavelengths and then running smoothing through them or cleaning them up. Nice. The VFOT tool is fun. So if you want to take photographs, astro images of variable stars, this will allow you to take your FITS format imagery and analyze it and actually measure the brightness of the stars off the images. And so this is the sort of process that, Samantha, that you guys would use for detecting exoplanets, right?
Mm-hmm.
You
just
actually,
I was reading up on this. To be able to use this tool, you do need to be an AVSO member to use the VFOT. If you have some FITS files and you want to try, we also use for the robotic telescope with classrooms. We use Astro Image J to measure photometry. Now you have to kind of understand what you're doing to specifically make it analyze variable stars. But yeah, this is a cool tool to have it online as well.
okay, next up is the variable star plotter. This is what you want to use when you want to make a sky chart to go out, take out with you to see your variable star. And there are quite a few parameters in here that you can set. Most of them you can leave alone. So what did we say? We said Omicron Ceti. So I'm going to give a star name. I'm not going to worry about its coordinates, although I could type in its coordinates instead if I wanted to. Those letters A, B, C, D that I mentioned a few minutes ago, they're in this little drop-down menu here. You can see that A gives you a field of 900 arc minutes, which is, what is that, 15 degrees. And then you could go to half of that, 3 degrees, 2 degrees, 1 degree, and so on, down to telescope eyepiece scale. So if I pick the A, you can have a visual chart, reversed, or CCD. You can plot for chart or photometry. You can even save the name of the chart to come back later and grab it again. So if you head on down here, you can set the magnitude limit. If you want to make the chart more cluttered, less cluttered, you can adjust that. So I put 9, 150. You can label it. So I could put in Myra here. And then you can decide the orientation. So for binoculars, generally you want north is up, east is left. So that's nothing flipped around. If you've got, a telescope and you're planning to look through the telescope with the chart, then you want to choose whichever orientation will match. Down here, we can leave everything else alone and we can plot. Let's see what we get. It's thinking. Okay, here we go. So when you get the chart, it's labeled Myra. You can actually click on it to make it bigger. I think you can keep clicking to make it bigger and bigger. You can print it out or whatever you like. Now, what you're seeing in here are the dot sizes are representative of the brightness of the star, as you would in a regular sky chart. But the numbers here represent the magnitude, the visual magnitude of the star times 10. So this would be a magnitude 3.5 star, a 4.1, 6.3, and so on. The star you're focused on isn't plotted with a dot because they don't want to bias your judgment about how bright it is. So they're asking you to compare Myra with the magnitudes of the stars around it. And you're going to interpolate. So you're going to find a star that's brighter and check its magnitude. You're going to find a star that's fainter, check its magnitude, and then mentally try to interpolate between the two to estimate what you think the visual magnitude of the star would be. So that's how you use these charts. I'll go back and do this again. You can also choose a binoculars chart. And this should be a little less detailed. So it's fewer of the stars have the magnitudes on. So I'll give you an example I made for Shelliac. And then we'll compare that with the Stellarium view. Okay. So Shelliac is the star near the Ring Nebula. right? So this would be the bottom of the parallelogram of Lyra. Unfortunately, they don't connect the lines for you on these charts. If you want lines, you can draw them on later on. So let's go to Shellyak and see if we can compare this. So we'll go to Shellyak on this. And I'm going to go north up. And so if I switch between these two, so you've got Bright Star down here and then Shellyak. And we'll go back to that. So Bright Star down here, Shellyak, and then there's 2 stars below. So these are the 2 stars below. So you get the idea of how this would work. All right. I think that's okay. Let's go to the couple more little tools that you can use on the AVSO website. The V-star is a way, again, if you're a member and you want to work with data, you want to analyze the curves, you want to fit polynomials through them, this is the portal to do that kind of work, more scientific analysis work. And then last up is WebObs. So if you're wanting to contribute to science, you can actually make an account. I don't believe you need to be a member to make an account to submit observations. You just get yourself an account, you get a user identification, and then you can submit your observations. And then you can also later go on and plot your observations up. And you can, when you go to your chart making process, you can actually select your own observations and highlight them and compare them to other observers and do things like that. So it's a lot of fun. I hope everybody is interested in giving it a try. All right.
I'm going to put a plug in. If you end up enjoying this, keep your eyes out for the course that we will be running with the RASC Robotic Telescope in the early year, it'll be limited registration. So stay in tune with all the RASC communications, and we're going to go from the basics of what is a variable star all the way to you be working with real data we collect from the robotic telescope. So that would be a cool chance if this is something you want to get into as well.
Nice. Any final questions before we switch to Messier minutes?
We have someone looking for, can you show a photometry table? What do you, I'm just asking that person, what do you mean by a photometry table? What would you like?
Well, a photometry table would be comparable to the parameters that are plotted on the curve listed in numerical form. So every circle or every symbol on that chart represents a numerical brightness value. And you could plot them in a data set. You could put them into Excel. You could fit a curve to them. You can manipulate them. And they can be your observations. They could be just the observations in the public domain. I think that may be what they're asking about.
Okay. It says when using CCD. Was this on the AVSO website?
If I go to the, let me just go back to the tools here, analyze here. You'll see, so you'll get, they'll take measurements. So essentially what the analysis tool does, go back to you, I think you're talking about the VFOT here, photometry tool. So essentially it takes the image, looks at the bloat of the image of the star, and it is able to match that to an apparent brightness. And that'll produce a number for that date and time. And if you take that image, a number of those images over a number of different nights, you'll be able to eventually produce a list that shows that star varying in its visual brightness. I think that's kind of what you're driving at.
Mm-hmm. David Lee also says sometimes photometry tables are used for identifying comparison stars.
Yeah.
So,
yeah.
Thank you. Any other questions about variable stars? Speaking of, forever hold your peace. Are we ready for the next stage? Our second, if I get this correct, second last
Messier minutes.
We have 5 today and 4. We're down to like less than 10. Has everybody actually observed the 100 we've gone through so far?
Yeah. So
Oh.
I don't remember the date, but we actually started Messier Minutes with autumn targets. So what we've done now is you've gone full cycle, and we're ready to finish the I guess
I can
12
tell
or
you
so that we missed.
the exact date we started Messier Minutes was February 1st, was the first one we went through. And we did some autumn targets that you could catch in the early evening. So
That's right.
if you are looking for Messiers to view right now, and because we're getting to the autumn, go back to the beginning of the series we did and see what we talked about there. We don't talk about
That's right.
what you are up right now. And with that, let's start.
Yeah, no, that's a good point. So the Messier Minutes, you can think of it, don't think of it more as to the date, the month and year we uploaded it. Think of it just in terms of the month and date, not the year, because it's perpetually recycled. All right.
And each Messier guides has the week based on what we did it, so you can go back and see the days that we looked at them. It's all there in the link I shared in the chat.
So I'll just start out by pointing something interesting. So this is the Stellarium chart for this evening around 11 p.m. with symbols on all the only on the Messier objects with their names and designations. And you might notice that there's our friend Jupiter sitting there in the middle. There's a kind of a gap with no Messier objects in it. And that gap is the reason that the Messier Marathon works. So there's a time of the year when the sun is sitting in this gap when you can catch, these ones before dawn, and you can catch these ones after sunset and not miss any others because there aren't any beside the sun. So that's where the Messier Marathon works. So we're actually, when John designed the 110 Things book, we worked with the order of objects to view, and he started the book off with autumn because he was thinking of the Messier Marathon, how it, it kicks off, kind of kicks there's that gap, and you can get into the autumn targets and move through the year that way. So here we are at towards the end of September. We've got a moon in the sky this week, but these objects will be around for a while, so you can catch them now or wait till the moon disappears. Most of these objects are quite bright though, so the moon is not going to bother us very much at all. I'm just going to switch Stellarium to show the designations. So we'll get here we go. Here we go. So now I've got the M numbers showing up. First up, I've got M15. M15 is up here over the southern horizon around 11 o'clock, but of course it's a little bit to the east of the meridian in the late evening. And this is a globular cluster, and it's kind of like the oat bag that Pegasus is munching on. So Pegasus is the horse, he's upside down. This is his neck, his ear or eye, and then his muzzle with the star Enif. And then he's munching on this nice flower or globular cluster, however you want to think of it. So this is really an autumn showpiece, Messier 15. It's relatively bright, magnitude 6.3. You can see it in binoculars on a dark night. You can see it in any size of a telescope. It's easy to find by using that line between Pegasus's eye and his tip of his nose, and just basically jumping another half of that span in that same direction. Basically what you're doing, Pegasus sort of rotates around as the sky rotates through the year. So essentially you're going to be heading towards Albireo. So there's Albireo, there's the summer triangle. So just if you find NF, then just remember that M15 is towards the summer triangle side of that star.
Just a quick correction. We mentioned the moon was up because I think you got confused because your bookmark was on a different date. The moon is actually in the waxing crescent phase, evening sky, but there's not much of a moon for the next week.
Yeah.
So you'll be
I may have pointed at the moon, but my words were referring to the tonight's.
Yeah. Sorry, just wanted to make sure everybody was.
Yeah. Here we are back to tonight. Yeah.
There we go. See, it doesn't change that much.
No.
Yeah.
Yeah.
So the moon will be up in the evening sky, but it won't be full, unlike it was a couple weeks ago.
All right. So yes. So as I said, you can find it by extending that line up past NF. When you're there, I'll just bring it up in the telescope view here. This is simulating a 6-inch Dobsonian reflector with a 26mm Plossl eyepiece. You can look for kind of a triangle of field stars bracketing it. Check out the cluster shape. You want to note that. You'll probably notice that its core is very dense. It has a collapsed core. We talked about globular clusters a couple of months ago. And then you want to crank up the power. So if you want to be able to peer inside the center of the core, you really need to increase the magnification. Look and see if you see any differences in the star colors. And while you're looking, think about the fact that there is possibly a black hole in the center of that collapsed core globular cluster. It's really a cool object. It's 32,000 light years away from us. That's M15. M2, and again, these are great objects for the suburbs. They're bright enough to see, on your driveway in the suburbs. So M2 is another showpiece. It's large, it's bright, visible in binoculars, any telescope. It's kind of in an empty patch of the sky, though, unfortunately. What I use is I go 2/3 of the way from NF to Saddle Sud. So if you've still got NF in your mind from looking at M15, you want to sort of come down this way and see if you can find Saddle Sud, which is part of Aquarius, and it's kind of on that line connecting them. So yeah, about 2/3 of the way along that line. And again, big enough to see in binoculars, so you should be able to have no problem finding it. If you are using binoculars, they'll actually share the same field of view. So you can actually put the star and the cluster in the binoculars together. You want to look and see whether you notice that it has a non-round shape. So it's got some surrounding streams of stars that you might see extending outwards, maybe like octopus tentacles or something like that. Again, crank up the magnification to try to delve into the center of the cluster a little bit more. You want to look for, see if you notice any stars of different colors. Again, note the density profile. And this one is actually known to host 21 variable stars, Cepheids, RR Lyrae, and RV Tauri variable stars in this globular cluster, 39,000 light years. So that was fitting that we're looking at this one today. That's M2. Heading downwards, and I'm going down, I'm looking at the higher ones first because they'll be higher in the sky in early evening. And these lower ones take a bit longer to climb higher. So tackle these M15 and 2 first, and then dive into the last 3. So we've got M73 and M72, which are sitting up here above Capricornus. And when I see these stars in the sky, I always sort of think of a bikini bottom. So I don't know, that's different, but that's what I see. And this year, Saturn is sitting just tucked above the waistband of the bikini. So that'll get you into the neighborhood. And these 2 objects, one is a globular cluster, one is an open cluster, sort of. They actually share binoculars field of view. I think they may even share the eyepiece at low magnification. So M73 is actually kind of a disappointed. It's not a deep sky object, it's an asterism. Messier thought he perhaps saw some nebulosity around this little Y-shaped set of stars. And so he put it on his list. But yeah, it's not gonna break any records for deep sky in that case.
So is it actually because it says open star cluster on this. Is it an open star cluster or just it looks like one?
Well, it's categorized as an open star cluster here in Stellarium, but if you look up the data on it, some sources consider it just an asterism, a line of sight. The stars are at different distances away. Mm-hmm. They just happen to be aligned, so we can see them in a clump. Yeah, and you'll want to crank up the magnification. So you can see that this is the same field of view I used for M2 and M15, and it's barely noticeable in the center of the view. So you really want to crank it up to about 100 times 100x to really see it. Where is it? It's about a thumb's width apart from M72. And the way I sort of would guide you is to use Theta Capricorni to Albulans. So where are we here? This should be. So from this star down to Theta. So this is Theta over here. So if you start at Theta with the star that's near Saturn, then it's sort of near that line connecting that to the fingertips of Aquarius, the western fingertips of Aquarius. So what you can do when you've got it in your sights is you can, describe to the stars all look the same. Do you see brightness differences, color differences? Note anything around the object, and that sort of a thing.
I was just looking at a picture we took of it in our robotic telescope, and it's very underwhelming. Like, you could easily pass by it. So that might be a warning for people looking for it, that it's very small, even with the the narrower field of view we have with our robotic telescope.
Yeah, that's that's a good reason to have a little bit of context and know what to expect to find around these objects. Okay, M72 is definitely worth going for. It's another globular cluster, much smaller than the first two I talked about, though. It's very far away, 54,000 plus light years away. You won't be able to get this one really in binoculars, but you'll want to use any size of a telescope. Small telescope will work. Small telescopes will see it as a fuzzy patch. A medium aperture telescope will start to resolve the globular cluster form of it. But you really need a 10-inch or something like that to see resolved stars in the cluster. It's pretty small and distant. As I mentioned, you can again sort of use some of these bikini stars to find it. So again, if you start at Theta, if you find M73, then you could just nick a little bit to the west for M72, or you could use the belly button of the bikinis and going up, and it's on that line connecting those two stars. So you'll probably notice also that it doesn't have a very dense core. It's quite a sparse cluster when you start magnifying it. And you'll want to say remark on any field stars you see around it. Any general ideas about the shape, that kind of thing. Okay, and our last one is down here below Saturn. So this is only good for this year because Saturn will be here next year. But for this year, we have Saturn and Vesta in the neighborhood of M30. M30 is the object that we can't really get in the Messier Marathon. Just the geometry for Canada makes seeing Messier 30 nearly impossible. So
we didn't even get it.
Yeah, it's probably
on our telescope.
Yeah, it's going to be the one that got away typically. But hey, take a look at it when it is in the sky. Because it's rather low, it's a tricky one for Canadians. It doesn't rise very high in the sky. It's only, for Toronto, it's only culminating at 22 degrees towards midnight. If you can see the star Fomalhaut in Pisces Austrinus, then that can kind of, then you're guaranteed that you're going to be able to see it. But in a lot of places in northern cities in Canada, a lot of northern places, the horizon would be a lot higher than I'm showing. So what you've got in the case of M30 is a medium-sized globular cluster. It's culminates around 10 p.m. nowadays, so that would be the time to set your alarm and look at it then. You can see it in binoculars when it's near its high point. Any size of a telescope will work. I noted that it had some field stars nearby, including this one here I'm pointing at, that made it seem like it wasn't round. It sort of made it appear to be elongated. You will also be able to see this magnitude 5.2 star 41 Cap in the same field of view of your telescope. So that'll actually help you guarantee that you're seeing the right neighborhood. There's that 41 Cap star. When you're looking at it, you want to look for, use higher power to resolve the structure. You want to look for its shape, look for the distribution of those stars that I mentioned around it. It's about 27,000 light years away. So that's your set of medium bright, moon tolerant Messiers for autumn. And then next time we'll do our final 4.
Does anybody have any questions from Messiers? Has anybody actually viewed any of the Messiers we've talked about today? Oh, Chris. I'm still working on the easy ones. Well, we hope you're learning something, as well as always, we shared the link for our Messier Minutes document. That's always there. We will also be linking. It's going to be a little delayed for me to edit down the 15-minute segment here, but we will have that linked as well on our website. And just to remind everybody, we are back to bi-weekly sessions of Insider's Guide. So our next one is the 11th. Yes, it's the 11th, right after Thanksgiving weekend. So
I think what I planned is to demo all the really cool aspects of the Stellarium mobile app. So it's one of those apps where it looks great and it does its job, but there's lots of powerful features that are hidden away that if you know where to click and how to bring them up, you can do a lot more with it. So it's a great time to
download that app before next time. Check it out. I found it a little overwhelming at first, so I'm very excited for this. And yeah, that's awesome.
Very good.
I think we got a lot of thank yous. That's about it. Thank you all for coming and joining us every single week we do this. Okay.
Yeah. And keep looking up and wishing for clear skies in autumn before the weather.
And have a great International Astronomy Day this Saturday.